This online lecture will be about coordinate systems, and in particular, how to convert between different coordinate systems. I will start by working things out in detail in 2 dimensions, namely for the Cartesian and the polar coordinate system. The next video will then be about 3 dimensions, where I'll introduce you to the spherical and the cylindrical coordinate system. The simplest coordinate system is one which you're all familiar with, namely the so-called Cartesian coordinate system. And this is actually probably the most widely used coordinate system, which you can use to describe a point in n-dimensional space by n real numbers. Namely that the point x is described as a tuple x, or as a vector x1, x2, up to xn. And what makes this Cartesian coordinate system particularly simple is that you have basically straight coordinate axes here. So I can only show it in 2 dimensions. So that's what I'm doing here. Namely a coordinate axis in x direction and in y direction. They're simply straight and they form a orthogonal angle. And a point x in this coordinate space is described by, in this case, 2 dimensions by 2 numbers x1 and x2. Now, what makes this Cartesian coordinate system particularly simple is that all directions are simply straight and orthogonal to each other. And that makes it very easy, because then, for example, if we have this situation here, we have 2 points in this space described by 2 different sets of Cartesian coordinates. It's very easy to calculate the distance between these 2 points, because if we have that this distance here is denoted as dx1, so that's the difference between the x1 coordinates, and this distance here is denoted by dx2, then because we have a 90 degrees angle here, we can simply use Pythagorean theorem to calculate the distance between these 2 points. Namely, the distance is then simply given by ds squared equals to dx1 squared plus dx2 squared. What is also simple is, in this case, to calculate volumes. So if we're now not interested in the distance between these 2 points, but if we're actually interested in the volume or area in 2D that is spanned by these 2 distances, dx1 and dx2, again, because we have orthogonal directions here, we simply have the volume of a rectangle. So we also know how to calculate the volume, and it simply is dv equals dx1 times dx2. So why am I actually talking about the volume here? Why is it interesting? It's actually interesting because, you actually see it right from my notation. So, actually what I'm saying here in Cartesian coordinates is true for arbitrary distances dx1 and dx2. But when we talk about integrals, we always talk about infinitesimal distances. Yeah? So you want to, in an integral, you kind of sum over an infinite number of very, very small volumes. And well, for the Cartesian coordinate system, this integral over the volume, that is then, from what you just saw, of course, very simple, because it simply is an integration over the different coordinate directions. So here I'm again writing it with an arbitrary n-dimensional space. So what we want to do now is we want to see how does that behave when we go to different coordinate systems. And you already see here on the bottom of the page, already peeking out what we're going to look at next is the so-called polar coordinate system, which you'll actually recognize is very much related to what we did for the complex numbers. So how are polar coordinates defined? So just to remind you, in polar coordinates, we define a point x in 2-dimensional space. So polar coordinates are now only applicable to 2D space by the distance from the origin, which is denoted by r, and by the angle phi that this vector makes with the axis x. And then, well, easily you can see from trigonometry, you can see that the Cartesian coordinates which are x1 and x2, or in this case, because we're talking about two-dimensional space, we're simply calling them x and y. They're simply given by r times cosine theta and r times sine theta. So y is r times sine theta. So in that sense, what we already see here, what we have, so these formulas here, they are formulas for converting between different coordinate systems. So if you know the point in polar coordinates, so you know r and phi, with these formulas, you can convert to Cartesian coordinates. Now, of course, we also want the opposite. We also want to be able to, if you have Cartesian coordinates, to convert to polar coordinates. And there the formula is again a little bit more complicated, but you'll just recognize it's actually the same as we had for the complex numbers. Namely, we have that r is given by the square root of x squared plus y squared. So that is simply the length of the vector that is that has the Cartesian coordinates x and y. So this is actually very simple again. And for the angle phi, we need to again look at you know, the ratio between x and y, which gives us a tangent. And then to get the angle, we need to take the inverse of the tangent, and that is the inverse tangent or arc tangent, as is denoted here. And then again, we just have to be careful again with the yeah, which branch of the tangent we were on, because the tangent takes the same value for multiple angles. So that's why we have to do this differentiation here, where we basically have the case x larger than 0, x smaller than 0, and y larger than 0, and x smaller than 0, and y smaller than 0. Again, it's easiest to just think what this actually means. And what it means is that if you're in the upper half plane, then the angle phi is defined as positive. If you're in the lower half plane, then the angle is negative. So this is, you know, again, as for the complex numbers, this is a particular convention that we chose here. In principle, you can choose a different convention. You just have to stick to one. Now, this is how you can convert between these coordinate systems. So basically, so these were convert from polar to Cartesian. These are from Cartesian to polar. How does it now look with distances and volumes for polar coordinates? So, you know, to look at distance and volume, we have to again look at least at 2 points in 2D plane. So what I denote here is I have these 2 points in the 2D plane. And so the 1 point here is described by the length r, but the distance r from the origin. And the other point is actually away the distance r plus dr. And so for distances and volumes, I will not actually have to specify any absolute angles, but what I see here is that these 2 points, when I look at the angle that is between these 2 vectors, that one I call d phi. And well, you know, if we do that, then we see that, you know, we have now these arcs here, this arc, and these straight lines. So it's easy to see, of course, that the length of this line here is also such just dr. And the length of these 2 arcs here is, so this arc inside here, that length is r d phi. So yeah, so basically you have the distance r from the origin and the angle that is spanned, that is d phi. And here, that arc here has length r plus dr d phi. So that arc here, that is actually a little bit longer than that arc that we have down here. Now that is when we have a general, you know, lengths, you know, arbitrary lengths. Now things become simpler if we go to infinitesimal length dr and infinitesimal angle differences d phi. So let's do that. Because what happens then is that if we go to an infinitesimal dr and d phi, we can actually neglect the length difference between these two arcs here. So in this case, this length here will be r d phi. This length here will be dr. And the other sides, they simply have the same length. And because, you know, in the polar coordinates, also here in this particular case, you know, the angles that we have locally in this coordinate system are still 90 degrees, we actually end up with a simple rectangle with all the opposite sides having the same length. And then we can again do the same as we do for Cartesian coordinates and calculate the length as the distance between the 2 points as ds squared equals to now dr squared. So first this side here, and then we need to also take plus the square of that side, and that is plus r squared d phi squared. And if you want to calculate the area or the volume element, then it is simply given by the product of these two sides. So that is dr times r d phi, or as it's usually written, it's r dr d phi. And this is the volume element now is again important for calculating integrals. And let's just show a very simple example. We want to calculate the integral over a disk in space. So basically here, the whole area in this two-dimensional circle. And, you know, I mean, it's, you know, here we have a circular object, so it's clear that this will be much easier in polar coordinates than if you would want to do that with Cartesian coordinates. It's also possible to calculate this integral that I'm doing now in polar coordinates and Cartesian coordinates, but it's just more cumbersome because, you know, we're not taking advantage of the symmetry of the object that we have. So that is the generic advice, of course, always, you know, choose the coordinate system in which what you want to do is the easiest. And typically it means, you know, adapting to the symmetry of whatever you have that you want to describe. And, you know, a circle is just easiest described in polar coordinates. So how do we do this integral? Well, you know, we want to integrate over, you know, r dr d phi. So, you know, I'm saying that the function that I'm defining on that, you know, usually you integrate a function. Here I just want to integrate the constant function equals to 1. Yeah, so that doesn't appear here. What I want to show mainly is, you know, what kind of integral boundaries do you have to take? And, you know, so let's say we do first the integral over dr. So that integral has to go from the center up to the distance, the radius of the circle here. So that is from 0 up to r0. So that's what we have to integrate. So this radial distance here. And then we still have to integrate over the whole angle phi. And for the circle, we have to go around once. So we have to go from 0 to 2 pi. Now let's do this calculation. So the first integral, well, what you see first is that, you know, there is actually no, the variable phi doesn't appear in the integral. So it's actually, you know, for this integral, phi is a constant. So that's easy to integrate. So we just have integral from 0 to 2 pi d phi times integral from 0 to r0 r dr. And that first term, we just know it's going to be 2 pi. And the second term, what we know is, well, we're integrating over r. So the antiderivative of r is 1/2 r squared. So we have to take 1/2 r squared and now enter the boundaries 0 and r0. So in total, we get 2 pi times 1/2 r0 squared minus 0, but that you don't have to write. So if we collect everything together, we get pi r0 squared. And this is, of course, just the area of the circle. And that's what we're supposed to get if we integrate just a constant 1. because then the integral will just give you the area over which you're integrating, and that's pi times r0 squared.